So here are going to be a few math examples of some of the problems that you might be seeing in this chapter. And we're going to be looking at heat transfer and specific heats and those types of ideas. So question number one is kind of the most basic of the questions. How much heat must be added to a 20.4 gram sample of gold to increase its temperature by 8.3 degrees Celsius? And the specific heat of gold is 0.13 joules per gram degree Celsius. Now, the formula that you are going to be using is going to be Q is equal to Cm delta T, where C is the specific heat of the substance we're working with, M is the mass, and delta T is our change in temperature, and then Q represents the heat energy that we're going to be working with. Now, one thing that you do have to be careful about when you're doing these problems is you have to pay attention to the labels, and you have to make sure that the labels match so they will cancel out appropriately. So what I mean by that is, notice in this one, our sample is given to us in grams, and our specific heat is also given in grams. Now, if that was not the case, let's say that our sample was given in kilograms, we would first need to convert that into grams before proceeding with the question. So you do always want to make sure to check that your labels are going to line up right. And the best way to do that is to include the labels in your computation problem. So we're trying to find how much heat. We're trying to find Q. We need our specific heat, which is 0.13 joules per gram degree Celsius. We are going to times that by the mass. So we have 20.4 grams. And then we are going to times that by the change in temperature. And so this is another part that you have to watch out for. We are looking for the change in temperature. Sometimes they will just give you the starting temperature and the ending temperature. Well, to find your change, you would have to subtract those two values. In this case, they are telling us what the change in temperature was, that it was 8.3 degrees Celsius. So we don't have to do any subtraction for that one. They just came out and gave it to us. Now, before you start, you want to start looking at your labels. So, since we have a fractional unit, a rate in our first one, a lot of times for students it's easiest to turn these other items into fractions by putting a 1 under them if they are not also a rate. And now you can see that the grams from our top here cancel with the grams on our bottom, the degrees Celsius cancels with the degrees Celsius, and we are only left with a unit of joule, which means when we do this computation, we are computing the amount of heat in joules, which is fine. Okay. Once we get all that taken care of, now we can actually just go ahead and multiply our values together. So take 0.13 times 20.4 times 8.3, and that turns out to be Q equals 22.0116. Our label is joules, but we do need to take care of significant figures. We have 1, 2, 3, 2. So we get to keep 2 significant figures, so I would only put this in as 22 joules. Okay, now on our second one, I'm going to give myself a little more space here. It says a 92 gram piece of iron that is at 70 degrees Celsius is dropped into a container of water at 20 degrees Celsius. How much water was in the container if the temperature change of the water is 8 degrees Celsius? And then I give you the specific heat for each of those. So in this one, now you have to be thinking about conservation of energy, because we have two substances and they each have different starting temperatures, different masses, and all that type of stuff. So one thing you might want to do is first list out your values in 2 separate columns. So we are looking at iron and we are looking at water. So our iron, we have a 92 gram piece. Okay, in our water, we don't know how many grams there are. That's what we're going to end up trying to find. Okay, our initial temperature, so I'm going to call that T sub I, for the iron is 70 degrees Celsius. Okay, and the initial temperature of our water is 20 degrees Celsius. All right, so check, check, check. Okay, and then it tells us here that the temperature change of the water is 8 degrees Celsius. So I know that the final temperature of my water is going to be 28 degrees Celsius. Now it doesn't come out and say this directly, but that also tells me that we are going to have a final temperature of our iron of 28 degrees Celsius, and we are making the assumption that the two pieces have come to an equilibrium point so that they are both at the final same temperature. If we did not get to make that assumption, they would have to tell us specifically in the question what the final temperature of the iron was. So what we're going to do first is you'll see that we have the necessary components to compute Q for the iron. I'm just going to put a subscript of I for iron. Now again, I need to take my specific heat, and notice this time it's in calories per gram degree Celsius. So I would put in 0.11 calories per gram degree Celsius. So I'm still using that same formula up here, Q equals Cm delta T. Then my mass is in 92 grams. Now you'll notice again, my units match. My grams and my grams will cancel out. And then my change in temperature. Well, this time I know the starting temperature is 70 and I know the final temperature was 28. So that is a change of 42 degrees Celsius. So you do have to subtract those two values this time. And again, my Celsius will cancel out. Let's see, go ahead and multiply all that together. And I get the heat energy for the iron to be equal to 425.04. And this time my label is going to be calories, because that was what was left up here in my unit analysis. Now, I'm not going to round this value yet because I'm not done doing my computations. But what I can do is I know that this heat energy here that was essentially lost by the iron, that was, transferred out of the iron, is what was gained by the water. So when I start doing my setup for the water, this heat energy is going to be the same for the water. So I'm going to start with my 425.04 calories is equal to, and again, I'm using that same formula from above, which says I need to take my specific heat. Now you'll notice up here the specific heat of water is 1 calorie per gram Celsius. So I'm going to have 1 calorie. The mass, that's my unknown part, so I'm going to leave it as M. And then my change in temperature was 8 degrees Celsius. So my Celsius is going to cancel out. My mass is going to be in grams when I'm all done, and that will take care of those labels. And then you'll notice my calories will end up canceling out here in just a second. I'm going to give myself just a little more room again. So when I start to do this computation, I'm going to go ahead and multiply the right side of my equation here together. So I'm going to take my 1 calorie times M times 8, and that would end up giving me a numeric value of 8 calories. And then my M, I'm not actually going to put it together with that. I want to kind of keep them separate right now. And that's still going to be equal to my 425.04 calories here. Now, in order to solve for M, because it's being multiplied by 8 calories, I need to use the inverse operation, which is division, and I need to go ahead and divide both sides by 8 calories. Now, over here, that will completely take that out. On my left-hand side, you'll notice my calorie labels cancel out. And when I divide that 425 by 8, of course it moved it, I end up with 53.13 is equal to my mass, which is in grams. So 53.13 would be the amount of grams that I have to have in this water. Now again, we need to go back and check for sig figs, and it looks like we only get one significant figure, so we would want to round that to 50 grams. So there would be 50 grams of water in that particular example. Okay, number 3. Number 3, we have a 50-gram chunk of 80 degrees Celsius iron is poured into a cavity of a very large block of ice at 0 degrees Celsius. Now this question says how much ice will melt. We're still going to be using the same ideas, but one thing that you have to recognize here is that now we're looking at how much ice will melt. When we are working with a phase change, we have to incorporate a slightly different formula that includes the value for the heat of fusion or the heat of vaporization, depending on which phase change you're entering. But to start with, we're still going to be taking our 50-gram chunk of iron. So here's our iron. And I need to go back up. I believe the specific heat was 0.11. Yes, so iron is 0.11 calories per, jeepers criminy, 0.11 calories per gram degree Celsius. That is the specific heat of iron from the problem above. So when I figure out the heat energy, I'm still using the original same formula, okay, because the iron is not going through a phase change. Only the water is, or the ice. So I'm going to take my specific heat. I forgot to put my labels in there. So this is calorie GC times my mass, which is 50 grams, times, okay, now here, my delta T. My starting temperature is 80 degrees Celsius. It doesn't specifically tell me the final temperature, but I am assuming, and we'll figure this out in just a little bit, that the block of ice is large enough that the entire thing doesn't melt. So that means the final temperature of my iron has to get down to 0 degrees Celsius. So my change in temperature would be from 80 to 0 degrees Celsius. That's also going to be a change of 80. Okay, my labels take care of each other. So notice this time I'm going to be working in calories again. Multiply those 3 values, and I get 440 calories. Now this is still going to be the amount of heat that goes into the ice, but what we're going to do differently is, because this is a phase change, our formula for a phase change is Q is equal to ml. And this is in your textbook in those math workout problems at the end of the chapter. It does take you through that second formula here. Now L represents either the heat of fusion or the heat of vaporization. In this case, we would need the heat of fusion. Sorry about that. But Q is going to remain the same. So I would take my 440 calories is equal to the mass, which is what I don't know, how much ice. And now the heat of fusion for ice, I had to look this up, is 80. Oh, this is going to be ugly. Sorry about this. Okay, so it's 80 calories per gram. Now you'll notice there's no temperature in this because remember, during a phase change, the temperature doesn't change. So when I solve this, I would divide both sides by 80 calories per gram, 80 calories per gram, divide that, and I turn out to get 5.5 grams is equal to my mass of water. Again, check for significant figures, and I would actually need to round that to 6 grams is my mass for my water on that one.